Today we are going to learn about mastering NumPy array manipulation techniques. We'll explore advanced methods of manipulating NumPy arrays to optimize data workflows, focusing on reshaping, splitting, stacking, and more.
Welcome to our session on mastering NumPy array manipulation techniques. In today's video, we'll delve into the advanced techniques of handling arrays using NumPy, an essential library for numerical computing in Python. Array manipulation is a critical skill in data analysis and scientific computing, allowing you to optimize workflows and improve efficiency. Throughout this video, you'll gain practical insights into reshaping, splitting, stacking, and more, empowering you to handle complex data preprocessing tasks with ease. Whether you're new to arrays or looking to enhance your skills, this session has something for you. Our journey begins with understanding array shape and dimensionality, fundamental concepts in NumPy. The shape of an array in NumPy refers to the number of elements along each dimension. For instance, a 2D array with 3 rows and 4 columns has a shape of 3, 4. Dimensionality, on the other hand, refers to the number of axes or dimensions an array has. A matrix is 2-dimensional, while a vector is 1-dimensional. Understanding these concepts is crucial because they dictate how you can manipulate arrays. The shape attribute in NumPy, accessible via array.shape, gives you a tuple representing the size of each dimension. This knowledge allows for efficient data handling, enabling you to reshape, split, or stack arrays appropriately. Consider an example where you have a dataset with multiple features. Knowing the shape and dimensionality helps in selecting the right manipulation technique, be it for reshaping into a flat array or maintaining the structure for further analysis. By mastering shape and dimensionality, you lay the groundwork for effective array manipulation.
Reshaping is a powerful tool in array manipulation, and NumPy provides the reshape function to change the shape of an array without altering its data. Whether you need to convert a 1D array into a 2D array or vice versa, reshape comes in handy. The syntax is simple: array.reshape new_shape. It's crucial to ensure that the new shape is compatible with the original array size, meaning the total number of elements must remain constant. For example, a 1D array of size 12 can be reshaped into a 2D array of shape 3, 4. Additionally, NumPy offers the rabble function to flatten multidimensional arrays into a one-dimensional array. This is useful for linear operations or when preparing data for certain algorithms that require flat input. Both functions, reshape and rabble, maintain data integrity, ensuring no data is lost or altered during the transformation. Practical applications include reshaping datasets for machine learning models, where specific input shapes are required, or flattening image data for pixel-wise operations. By mastering these techniques, you can efficiently adapt your data to various analytical needs. Combining arrays is a common task in data processing, and NumPy provides several functions to achieve this efficiently. The stack function merges arrays along a new axis, useful for creating multidimensional structures. For example, stacking 2D arrays along a new third axis can form a 3D array. The syntax is straightforward: np.stack array1, array2, axis equals axis_number. For horizontal stacking, where you need to merge arrays column-wise, use stack. This is particularly useful when combining datasets with the same number of rows but different features. Similarly, stack stacks arrays row-wise, ideal for appending new data samples to an existing dataset. These operations are vital in data aggregation tasks, such as merging monthly report data into a yearly overview or combining test results from different experiments. By leveraging stack, stack, and fstack, you can seamlessly integrate disparate datasets, enhancing your data analysis capabilities. These functions ensure that data alignment is maintained, preventing mismatches or loss during the merging process. There are scenarios where you need to divide arrays into smaller sections, and NumPy provides split and array_split functions for this purpose. The split function breaks an array into equal-sized subarrays. It's suitable when you know the array can be evenly divided. The syntax is np.splitarray, indices_or_ sections, where indices_or_ sections determines how the array is divided. For situations where equal division isn't possible, array_split comes to the rescue, allowing division into unequally sized parts. This flexibility is crucial in data partitioning tasks like dividing datasets for cross-validation in machine learning, where you might need different sized training and testing sets. Both functions ensure that the parts can be recombined without data loss, maintaining the overall structure's integrity. By mastering array splitting, you enhance your ability to manage and analyze subsets of data efficiently, facilitating tasks like batch processing and distributed computing. Transposing and swapping axes in arrays are essential operations in advanced data manipulation, particularly in tensor operations and multidimensional data analysis. The transpose function in NumPy is used to reverse or permute the axes of an array. For a 2D array, this means converting rows to columns and vice versa. This operation is crucial when aligning data for matrix multiplication or when adapting data to required input formats for various algorithms. Additionally, the swapAxes function allows for more complex axis reordering. For example, if you have a 3D array representing an RGB image with axes, height, width, color, you might need to swap the axes to color, height, width for certain processing tasks. These operations are widely used in fields like computer vision, where data alignment is critical for correct analysis and interpretation. By mastering transposing and axis swapping, you can ensure your data is in the optimal format for processing, enhancing both efficiency and accuracy.
Manipulating arrays often involves adding or removing elements, and NumPy provides insert and delete functions for these tasks. The insert function allows you to add elements at specified positions within an array. This is useful when you need to introduce new data points or features into your dataset. The syntax is np.insertArray, index, values, where index specifies the position for insertion. Conversely, the delete function removes elements from an array, identified by index or slice. This operation is crucial in data cleaning tasks, where you might need to eliminate outliers or irrelevant features. For example, removing a column of missing values from a dataset to improve the quality of analysis. Both insert and delete operations maintain array integrity, ensuring the overall structure is preserved. By effectively inserting and deleting elements, you can refine your datasets, enhancing the quality of your analyses and ensuring that your data remains relevant and accurate.
Efficient slicing and indexing are at the heart of data manipulation with NumPy, enabling you to access and modify array elements with precision. Slicing involves selecting specific portions of an array using the colon operator. For instance, array start-stop step lets you extract a subset of data, which is invaluable in tasks like time series analysis where you might need to isolate a particular time window. Indexing, on the other hand, allows for more targeted data selection. You can access elements by their indices, and NumPy supports advanced indexing techniques like Boolean indexing and fancy indexing. Boolean indexing involves using a condition to filter data, such as selecting all elements greater than a certain value. Fancy indexing allows you to select multiple elements at once using an array of indices. These techniques are crucial in data filtering and transformation tasks, ensuring that your analyses are both efficient and accurate. Mastering slicing and indexing enhances your ability to manipulate data with precision, enabling you to extract meaningful insights from complex datasets. In this section, we'll explore practical examples of how NumPy's array manipulation techniques can be applied to real-world data preprocessing tasks. Consider a scenario where you're preparing data for a machine learning model. Often, datasets come in various formats and structures, requiring reshaping to meet the model's input requirements. By using reshape and ravel, you can adapt your data to the necessary input shape, ensuring compatibility and enhancing model performance. Another common task is combining datasets from multiple sources. Using stack, and fstack, you can merge these datasets seamlessly, creating a comprehensive dataset for analysis. Splitting arrays is equally important, especially in machine learning, where dividing data into training and testing sets is crucial for model validation. Employing split and array_split, you can partition your data accurately, ensuring that your models are trained and tested effectively. These practical applications highlight the importance of mastering NumPy's array manipulation techniques, empowering you to enhance data quality and efficiency in your workflows. As we conclude our session on mastering NumPy array manipulation techniques, let's recap the key skills we've covered. You now have a solid understanding of array shape and dimensionality, and how to reshape, combine, and split arrays using NumPy's powerful functions. We've also explored transposing, swapping axes, and the importance of efficient slicing and indexing. These techniques are not just theoretical, they have practical applications in data preprocessing, enhancing your ability to handle complex datasets with ease. As you continue your learning journey, practice is essential. Apply these skills to real-world projects and explore more advanced topics in NumPy. By doing so, you'll further solidify your understanding and become proficient in data manipulation, a critical skill in today's data-driven world. Thank you for joining us, and we wish you success in your continued exploration of NumPy.